First of all, in this problem, problem number 4, factoring y squared plus 7y minus 18. What was your decision calculus here? How did you decide on the right way to fill out these two boxes that are the cross terms, the terms with just a y in them, for this factorization? What did you get here and here?
I got positive 9 and negative 2.
Positive 9 and negative 2. And that's a good pair because, first of all, they multiply together to give us negative 18. And what else do they do? They add together to give me positive 7. And that's good because then in my lattice, when I multiply everything out and I combine my like terms, I end up with a y squared, I end up with a negative 18, and I also end up with these middle terms, that are like terms, adding together to give me plus 7y. Great. So in the end, this factors into y plus 9 times y minus 2. So here's a question. What can we determine, what can we tell from the fact that this number, negative 18, is a negative number? What does that tell us about how we're going to be able to factor it, just from the outset? What do we know about the numbers that's going to multiply together and give me negative 18?
One of them has to be negative.
One of them has to be negative and the other one has to be positive. So that's the first thing that we notice here, is that our two numbers need to have opposite signs. We're going to have a plus something and we're going to have a minus something. Okay. Whereas in the kinds of problems we were looking at before, if we had a plus here, what would that have told us instead? They either need to be both negative or both positive, right? So that's the first observation that we can make, is based on the sign of the constant coefficient, we'll know right off the bat whether we need the two numbers that are going to win our sum and product game to have opposite signs, as they did in this example, or have the same sign, as they would in the example where that coefficient were positive. So that's the first thing to notice. Second, let's try and pull some lesson out of the sign of this coefficient, the coefficient of the first order term here, positive 7. What does the fact that that is positive tell me about the two numbers that are going to win my sum and product game?
That the larger number is going to be positive 1.
Yeah. That the larger number, the number with a larger absolute value, is going to be positive. Right? Because that's the sign rule for adding numbers with mixed signs, right? When I add two numbers, the sign of the sum is going to be the sign of the larger number, the number which has a larger absolute value. So in this example, the sum was positive, so I need my larger number, my 9, ended up with the positive sign. So of course, if this had been negative instead, what would the lesson have been here? The larger number is negative, yeah. So these are the considerations that go through my mind that are just informed by arithmetic, right? Informed by the sign rules for multiplication and the sign rules for addition, right? That can help, it helps me when I'm thinking my way through these problems to always keep those two things in mind. Let's look at this example next. Y squared plus y minus 20. Is there any reason why we would expect that this is going to be a slightly different problem than the ones that we've seen so far? Or is there anything different about this expression compared to that one? I chose this example because it's an example where the coefficient, the number, in front of one of my variable quantities, that the number wasn't explicitly written. In front of this y, there's a secret coefficient, and what is the secret? 1. So just don't forget that if you have a missing coefficient in front of a variable, that coefficient is a 1. So I would be looking here for a pair of numbers. Y squared is going to come out as y times y. Negative 20 is going to come out as factored by a pair of numbers which multiply together to give me negative 20 and which add together to give me positive 1. So what pair of numbers fits that bill? Positive 5 and negative 4. Those two have opposite signs because my negative 20 is negative. And the bigger of them has the positive sign because this coefficient is positive. Positive 5, negative 4. Sure enough, if I were to combine those, positive 5y plus negative 4y is going to give me positive 1y. And then I'm going to get my y squared and my minus 20. And so it works out. So don't forget about that kind of hidden coefficient. If there's a variable without a coefficient in front of it, write in the 1, just to remind yourself. How about this polynomial? Y squared minus 36. So how is this example different than the ones that we've seen so far? I'm still going to have my y squared here as y times y. Still going to have negative 36 in this corner. But now what's going on? What's missing?
You need two y's to cancel out.
Yeah, right, exactly. So what's different about this example is that I don't have, at least in writing, I don't have this middle term with a factor of y in it. I'm missing it altogether. And so that means that when I do all of this multiplication and I combine all of my like terms, that the terms in these two squares need to annihilate one another. Right? They need to wipe one another out so that we don't have them in our final answer. So whatever goes here needs to be exactly the opposite as whatever goes there. In other words, yet another way to say that is that if we think of there as being a missing term here in the middle, what is the coefficient of y that goes in this missing middle term this time? If we want them to cancel, we want that coefficient to be 0. So I'm looking now for a pair of numbers which multiply together to give me negative 36, but which add together to give me 0. What pair of numbers is going to fit there?
Positive 6 and negative 6.
Positive 6 and negative 6. Exactly. The signs need to be opposite because the product needs to be negative. But then the two numbers that we choose need to be mirror images of one another, equal and opposite, because they need to add together to give me 0. This is an example of a factorization that is in many textbooks called, it's almost lives in a different section of the chapter. It doesn't really need to because we know how to do it. Right? But it's an example of a factoring method that's often called the difference of squares method. And the reason it gets called the difference of squares is that we've cast the number negative 36 here as the product of a number and itself, 6 times 6. Right? This method worked because 36 was a perfect square. 6 times 6. Right? And so it gives us this pattern that works for any factorization. If I wanted to do y squared minus 81, how would that factor?
Y plus 9, y minus 9.
Plus 9 and minus 9, exactly. Where that 9 came from the square root of 81. Right? So that's the shortcut. And I think the reason it sometimes lands in a different section of the textbook is that they kind of like to teach people this shortcut. It's this little mental trick that can make this process, just lets you skip the step of drawing out the lattice and doing all that stuff. But I don't see them as separate techniques. It's all part of the same. It's all part of the same method of factoring that we've been talking about today.